Approximately 1 in 10 supernova explosions results in a magnetar. Most of these stellar collapses yield standard neutron stars, or pulsars, but specific environmental factors can force a different outcome. This process requires a massive progenitor star with a starting mass between 10 and 25 times that of our Sun. During the gravitational collapse, the physics must hit a precise threshold, a convergence of rapid rotational velocity and extreme internal temperature. The core of this newly formed object is an ultra-dense iron sphere. It contains a turbulent, superconducting fluid interior. Due to the conservation of angular momentum, the interior fluid remains in a state of highly energetic hydrodynamic chaos. Missing these exact threshold conditions produces a standard pulsar. This makes the magnetar a highly specific, extreme mutation of stellar evolution. This internal chaos drives the magno-hydrodynamic dynamo. Within the dense iron core, turbulent convection converts the star's thermal heat and rotational kinetic energy into raw magnetic energy. This cross-section shows the initiation of a runaway feedback loop. As the star spins, magnetic flux lines are continuously twisted and amplified by the fluid dynamics of the core. Accelerating fluid dynamics eventually lock into rigid structures, uniform geometric columns parallel to the axis of rotation. This force projects outward, extending far beyond the star's physical surface. The resulting magnetic field reaches 10 to the 11th Tesla. This field is 1 trillion times more powerful than Earth's. At this intensity, magnetism becomes the star's dominant physical characteristic. Standard stellar objects destroy matter through thermal radiation or gravitational crushing. A magnetar kills through pure spatial geometry. This lethal geometry is established by the 1,000-kilometer proximity threshold surrounding the star. Within this radius, macroscopic diamagnetism takes effect. The external magnetic force is powerful enough to physically override fundamental quantum chemistry. The magnetic grid dictates the shape and behavior of matter, bypassing chemical bonds entirely. When a macroscopic object crosses this threshold, it experiences complete structural dissolution without any heat or physical impact. At this proximity, magnetic geometry physically outlaws complex structure. Macroscopic objects cease to exist as distinct chemistry. In standard space, an atom is characterized by the spherical probability cloud of its orbiting electrons. Subjected to the magnetar's 10 to the 11th Tesla field, these spherical clouds are instantly deformed. The orbital compresses into a rigid rod, 200 times narrower than normal. Pushed past the de Broglie constraint, these cylinders become thinner than an electron's fundamental limit. This ensures total chemical failure. Parallel, needle-shaped orbitals cannot overlap to form covalent bonds. Matter dissolves into a highly organized, frictionless atomic plasma that travels along the magnetic field lines. Long before extreme gravity can interact with an object, the magnetar's field ensures the atoms of both biological and synthetic materials are geometrically disassembled. The surface of a magnetar is an ultra-dense iron crust layered over a proton superconductor interior. The 10 to the 11th Tesla magnetic field is physically anchored and locked deep within this very rigid iron crust. Over many thousands of years, the magnetar undergoes continuous spin-down, gradually losing angular momentum due to frame dragging and magnetic radiation. As the star's rotation slows, its geometry shifts toward a more spherical shape. However, the anchored magnetic field resists, pulling heavily against the crust. This creates macroscopic mechanical stress as the rigid crust absorbs the kinetic energy of the decelerating star. The iron crust can only withstand a finite amount of shear stress before it must violently adjust to a non-rotating equilibrium shape. The magnetar is caught in a contradiction between its solidifying physical structure and its decelerating magnetic grid, guaranteeing a catastrophic failure. This mechanical failure is a starquake, a sudden fracturing of the neutron star's iron crust. The physical shift is measured in micrometers and occurs in less than a millionth of a second. When the crust fractures, the anchored magnetic field lines are instantly severed. These lines violently whip back and reconnect, instantly converting the stored mechanical stress of the crust into pure electromagnetic energy. This micrometer shift transforms localized mechanical tension into the most concentrated eruption of energy physically possible. Astronomers classify these events as soft gamma repeaters, massive, irregular bursts of soft gamma and X-ray radiation. This radiation wave propagates at the speed of light, unmitigated by interstellar distances. In 1979, an impossible radiation spike was detected by interplanetary probes, including the Pioneer Venus Assembly. This was the first recorded megaflare from SGR 0525-66. In August 1998, a starquake from SGR 1900+14 sent a blast wave traveling 20,000 light-years across the galaxy. When the wave struck Earth, it bypassed orbital satellites and penetrated the atmosphere. The energy was sufficient to physically compress the ionosphere and ionize the nighttime side of Earth to levels usually reserved for daytime. A micrometer fracture on a 20-kilometer sphere contains enough energy to physically alter planetary atmospheres on the opposite side of the Milky Way. Magnetars represent the most powerful magnetic objects yet detected in the universe.